In this video, we're going to explain the genesis of faults and how faults affect the state of stress in the Earth crust. First of all, let's talk about the Earth crust and try to understand what the Earth crust is composed of. You may think that the Earth crust is a solid layer which is continuous, but it is not like that. The Earth crust, or really the Earth, inside the Earth, we have a nuclear reactor which has a power of more or less 20 terawatts. That's in the order of the energy consumption today on the entire Earth. So this power reactor heats up the rock, heats up the magma, and ends up on surface in movement of the tectonic plates. And that tectonic plate movement, as we have seen before, applies a tectonic strain on rock layers, which, if they get to the limit value at which the stress they can take, they are going to break. And therefore, the Earth crust is going to be composed by actually broken pieces of rock. This is kind of evident from the point of view of the tectonic plates. Each interface between tectonic plates is already a very large discontinuity in the Earth crust. But also that happens at a smaller scale through faults. And as I was mentioning before, we shouldn't imagine the Earth as a continuous slab of rock that, for example, might go from the entire state of Texas, let's say, to Oklahoma, but it is these are formed by geological formations which are broken at several scales. The largest scale will be the tectonic plates, but if you look inside also tectonic plates, we can also see faults. Like, for example, all these faults that I just visualize here on the surface of the state of Texas. And not to mention the faults that we have in the subsurface that we are not seeing here. But my point is that you should take into consideration and you should think about the Earth crust as an already broken geological formation, where those discontinuities are made of faults and fractures. And you can see this very clearly here in this area around Austin, that we have many faults that present discontinuities into the geological formations on the surface of this part of the state of Texas. Let me adjust the rock units, and then we complete the picture where we see that these discontinuities are clearly cutting through different rock layers. Okay, so how do these faults form? Why do they have the strike that we see here? What is the depth of these faults? This is what we're going to answer now. And the answer to that is related to the shear strength of geological materials. We have seen that the shear strength of geological materials is related to the friction coefficient. The shear stress is equal to the friction coefficient times the effective normal stress, which, if you put and rewrite in terms of the effective principal stresses, ends up with equation number 1, in which the maximum principal stress, effective principal stress, is equal to this parameter Q that goes from more or less 3 to 7 depending on the value of the friction coefficient. So sigma 1 is equal to 3 to 7, the least effective principal stress, sigma 3. But remember that this is the same as saying that shear stress is equal to friction coefficient times effective normal stress. But sometimes it's more useful to talk in terms of effective stresses and effective principal stresses, because in that way we can relate that to the in situ stresses in the subsurface. So faults are going to be basically shear fractures, and the same theory of shear strength that we saw before that apply at the small scale, it also applies at the larger scale and applies to faults. And in this case, since it is the same theory, now we're going to have that based on this shear strength theory, the maximum principal stress is going to depend on the least effective principal stress, and that's going to be proportional to this friction parameter Q. At the large scale, we consider that there is no cohesive strength or cementation because, as we said before, the subsurface is already broken into pieces. So at the large scale, there is no really a cohesive strength or a cementation which is holding all of this rock mass as an entire rock slab, but it's already broken into pieces. You may also think this similarly to the case of the cohesionless sand or a dry sand, which is not cemented. Well, in this case, this is made up of geological layers and rock formation which are already fractured, so there is also no cementation between them, and that's the reason why this intercept goes through zero. And this graph and this equation is quite important because it's telling us, let me move a little bit further down, it's telling us that the maximum principal stress depends on the least effective principal stress, both effective, through this parameter Q, which is something that we call a effective stress anisotropy parameter. For example, if you had a fluid, the effective stress anisotropy parameter is equal to 1. Why? Because in a fluid, the pressure has to be the same in all directions, and therefore the pressure or stress in any direction has to be equal to the pressure or stress in any other direction, therefore Q is equal to 1. Well, a property of solid is that that condition is not necessarily with this Q equal to 1, but you can have an anisotropy of stresses which are different in different directions. And what we see now is that with the theory of the shear strength, that anisotropy is not infinite, but rather has a limited value, which now we see that it's about 3 to 7. And that means that in solid materials, which are already broken into pieces and they have these continuities, the maximum stress anisotropy depends on the shear strength of the material and therefore on the friction coefficient, and the maximum is about 3 to 7. And this is very important because this is going to set a limit on the maximum stress anisotropy that I can have also on the Earth's surface. Here we can see that for different values of friction coefficient, as the friction coefficient increases, this parameter Q increases and the maximum allowable stress anisotropy also increases. We also see that this is related to the friction coefficient and it's related also to the failure angle at which I would expect such shear failure. Let me hold on a little bit on this. We'll come back to this failure angle in a little bit. Okay, so let's apply now the shear strength theory to the genesis of faults. And in order to do that, let me start here with one example, which is this one, in which let's imagine that we are placed in a long time ago, let's say 200 million years, and there is a brand new deposited sedimentary basin which it didn't suffer any tectonic strain so far, and all the layers are perfectly flat and perfectly horizontal. This is what gravity would do in a sedimentation process. Let's say that some time passes by and we have some mountain building around this region, but also, most importantly, we have tectonic strains which are applied in horizontal direction so that my maximum horizontal stress gets very high and actually gets higher than the vertical stress. If those tectonic strains are enough, I could produce a failure of these sedimentary layers that were originally not broken, but if I overcome the shear strength of such material, what is going to form is a fault. And notice that the orientation of such fault is going to depend on the orientation also on the principal stresses at such location. Let's continue a little bit more with this example, and let's assume that the stresses, the tectonic stresses, after failure, they continue to be applied such that after some time I have a displacement of these layers. The hanging wall moves over the foot wall, and this is a result, I hope you can see, of the stresses, because the stresses are pushing sideways, and this is causing a contraction in this region of the air crust in horizontal direction, and it's also making this part of this layer to go up with relative to this part. And what I have in the middle is a fault. In this case, this is what is called a thrust fault. And we'll come back to this example in a bit, but notice that this is following exactly what we have seen for shear strength for the failure of a rock under a triaxial condition, in which a fault or a fracture would form at a certain angle with respect to the principal stresses, which is steep with respect to the orientation of the plane where the maximum stress is applied. So this orientation is the same as this one. Let me show an example that it's a video that shows this process at a much smaller scale, but anyways, it's very illustrative. So let's go ahead. Let me go here into full screen. Here we have a sandbox experiment where we have several layers, and a tectonic strain is applied by God here from the right. And what this is causing is what we saw before. It's a shear failure at some point, and now the foot wall is moving, the hanging wall is moving over the foot wall. And you can see now there is a second fault that forms over here. And let me pause this right here. We see that this is a little bit more complicated than what we had before, because we have several faults or shear fractures, you could call it in this case, but also some of the sedimentary layers, they are not horizontal anymore and they start to fault. Well, this is what will happen in nature in reality, but this is already with quite a bit of tectonic strain. But what we see here is exactly what we have over here, and is what would explain a thrust fault. All right. The same process would happen to form the three types of faults that we're going to see. It's just that the stresses are going to be oriented in different directions. So the first example is the one of a normal fault. In a normal fault, we have a fault that forms under conditions in which the maximum principal stress is vertical, the minimum principal stress is horizontal, and a fault would form as predicted by the shear strength theory at an angle of more or less, in this case, 60 degrees if, let's assume, the friction angle equal to 30, so 45 plus 30 divided by 2 is going to be 60. The fault is going to form at an angle of dip of more or less 60 degrees from the horizontal plane with respect to the plane of the fault. And notice that the strike of the fault is going to be perpendicular to the minimum principal stress. Let's try to understand physically what's going on here. What is happening in this normal fault is that the maximum principal stress is doing the work to break this rock. And because this one is the maximum, this one is going to be pushing down this section because it is the maximum, and also the same stress and the reaction is going to be pushing up this section, and all of this movement is going to do work against the minimum principal stress. And that makes a lot of sense, because why would this fracture break and do work against the intermediate stress if the intermediate stress is higher than the minimum principal stress? The fracture is going to form at an orientation such that the movement is going to do work against the minimum principal stress. That's why the strike of this fault is perpendicular to the direction of the minimum principal stress, and also that's why the angle here of the dip is 60 degrees with respect to the horizontal plane. This is a normal fault, and this is what happens in a setting which are usually called an extensional setting, which has the two horizontal stress lower than the vertical stress. Examples of these type of faults are here. For example, these two are normal faults. Notice that always the hanging wall is moving down with respect to the foot wall, and these are called normal faults also because it makes a lot of sense that rocks will move down because of the action of gravity, right? Gravity will bring everything down. So if we consider this static, then this section, the hanging wall, is going downward relative to the foot wall. This is the same Moa fault that we discussed, or part of the Moa fault that we discussed in the previous lecture. And also you can see very clearly here that angle. The dip is quite steep, and it's about 60 degrees in both cases. These two are normal faults observed in outcrops, and here you have an example of normal faults observed in seismic, where you can see all these discontinuities marked in black are the faults, and also here we shouldn't trust what is the alignment of these, but if this scale was done in such a way, or this plot was done in such a way that more or less respects the scale in horizontal vertical direction, we would see directly from here the angle of these faults. Okay, let me come back over here, and another case of a normal fault is when you have two adjacent faults that cause in a normal or an extensional setting something which is called a graben. Sometimes these faults, they form in a way that we have a solution which are called conjugate faults. Do you remember when you solved the roots of a parabolic equation and you found two solutions for that? And furthermore, when that parabola was centered around the y-axis, your two solutions will be numerically the same value but with different signs. For example, positive 2 and negative 2. Those are what I call conjugate solutions. And with shear, it happens the same. We have two possible solutions here of the orientation of a fault, which numerically, for example, here in the dip, they are the same, but they go in different directions. But these two are possible solutions to the same problem. And what we observe here is something which is called a graben, which is something which falls in between these two faults. And in this example over here, also we see it, for example, in this region. This one will be a graben, which is in between these two major normal faults. All right. A normal fault then would happen in a normal stress regime, and that's actually where normal comes from the classification of faults. Let's see the second type. The second type is the one that we have already seen, which is a thrust fault. And in a thrust fault, what we would have are conditions in which the maximum principal stress is horizontal and the minimum principal stress is vertical. When you have such combination, then now the maximum stress is pushing sideways, and the shear failure that you would expect would be this type of failure over here, in which, let's apply the same logic that we did before, the block is moving along the direction of the maximum principal stress. So here the hanging wall is moving to the left and the foot wall is moving to the right, and this is doing work against the minimum principal stress, which is vertical, so this one is also moving up. So the hanging wall is not only moving left, but it's also moving up as these two parts move with respect to each other. And notice that this is moving up and not in the other horizontal direction, because again, the least principal stress is vertical, and it makes a lot more sense to have this moving up and do work against the minimum principal stress rather than do work against the intermediate principal stress. Let's look at the dip and the strike. Same as before, the angle now here is more or less 60 from here, from the plane of the maximum principal stress, now SH max, to the plane of the fault, and the strike of the fault depends on the direction, which is, in this case, perpendicular to the direction of these two, the maximum principal stress and the minimum principal stress. Here it's not that easy to see this, but it's going to be a lot clearer in the next section that we're going to talk about. But the strike is going to depend on that orientation, the orientation of the three stresses. Example of a thrust fault is the fault that I have over here, where you can see pretty much something very, very similar to what I show in the schematic, in which we have the the hanging wall, in this case moving over geological time from left to right, and the foot wall also moving from right to left. And also we can see that also some other conjugate faults and fractures that happen at the same location. This is what is called a thrust fault, and notice the dip. The dip is not as steep as in the normal fault, but it's a lot more gentle, because now the 60 degrees is not from the horizontal plane to the fault, it's rather from a vertical plane like this one to the fault. This is 60, and therefore the dip would be the complementary angle, this one, which in this case is going to be about 30, and you can see right away from this picture close to my hometown. All right, so let me come back over here. There is a special case of these thrust faults, which is called a reverse fault, in which you may have a normal fault, which is relatively steep, but that formed a long time ago under normal conditions, but now we have the stress that has changed over time, and what formed the fault is not the stress that I have right now, and in this example I have a switch of the stresses. Now, in this example, I have the current stresses to be correspond to a reverse faulting regime with SH max higher than SH min and SV. So now I have a relative movement of the hanging wall going up with respect to the foot wall. And this is called a reverse fault because notice that the foot wall is going up. If you consider this static and this one is going up, this is opposite to gravity, reverse to what you expect that gravity would do. And that's why it's called a reverse. So in this course, we're going to talk about reverse fault and thrust faults, which are more or less the same, although here's the difference, and they are not the same, but just, you know, to be compliant with the rest of the literature, we'll call the two of these reverse. And there is one more type of faulting regime, which is the strike-slip faulting regime. So what is going to happen with the strike-slip faulting regime? As we know, the maximum horizontal stress is going to be the maximum stress, and also a horizontal stress is going to be the minimum stress. So in this case now, a fault is going to form due to the combination of these two, SH max and SH min. And what we would expect is something like this, in which the fault is going to form along this region. And for now, just ignore the dip here. The dip for a true and ideal strike-slip fault is going to be 90 degrees. But just let's look at the strike. Notice that this strike line is going to be at 60 degrees from the plane where the maximum stress is applied, which in this case is SH max. And in this case now, there is no relative movement of the foot wall and the hanging wall. Actually, if it's 90 degrees, we don't have a foot wall and a hanging wall, but now we have a relative movement in horizontal direction of these two parts of the geological formation. In this case, we will say that if we jump from one side of the fault to the other, we can measure the movement, and in this case, it moved to the left. So this is a left lateral fault. Notice that if you were to jump from here to there, it would be the same. If we jump from here to there, we also see relative movement to the left. And the opposite will happen with the right lateral movement. Let's see an example of a strike-slip fault. Here I have an image where you can see a recent fault that form goes to an earthquake, and this caused an offset of this road. And what would you say in this case? Is this left lateral or right lateral? I hope that you can see that if we jump from here to there, there is a relative movement to the right. So this is a right lateral movement. And for this case, what I would expect is to have the, let's see, well, the horizontal stress to be going in order to cause this type of movement. Let me analyze this a little bit later for the right lateral. I don't quite see in my head. We're gonna solve it with the next problem that we're going to see. Okay, so let me come back over here, and we have seen before that we have named stress regimes according to normal, strike-slip, and reverse. And I didn't give you a good explanation about that, but now you see that this comes actually from the classification of faults. And the classification of faults is what allows me to call stress regimes in different parts of the world as a normal, strike-slip, or reverse. And this stress classification is very important because it not only allows me to understand what is going to be the relative movement of faults at given places around the world, but also what is going to be the geometry, for example, of hydraulic fractures. So just to take a little bit, to take a look at this map, I hope that you can appreciate that, for example, thrust faults here, let's see the caption in blue, happen in regions where you have intensive tectonic activity and mountain building, like for example here near the Andes or near the Himalayas, you see that thrust faulting, and in some other regions inside the tectonic plates, some other times you could see more normal faulting, like you see in regions over here, like we said in Texas, or you also can see around these regions and close to extensional plate tectonic boundaries using predominantly normal faulting. Okay, so now that we have seen what is the origin of faults, let's try to apply this to understand a little bit more in detail what would be the ideal orientation of faults and how, based on that, we can predict what is going to be the dip and strike of those faults as a function of the state of stress. This problem is going to have actually the reversed application that first, if we know what is the state of stress, we should be able to predict what is going to be the ideal strike and dip. But also, if you observe faults at a given location, you could predict what is the state of stress that caused such faults. All right, so let's go ahead then with this problem. Let's look at this three-dimensional block in which we have stresses applied, and these are all principal stresses, S1, S2, and S3, where S1 is larger than S2 and larger than S3. In this three-dimensional element, if I had shear failure, according to the theory of shear strength, I would have a fracture that forms at an angle beta from the plane of the maximum principal stress. And we have seen this in some of our experiments that we did in the laboratory. But let's add one more condition, because in the experiment in the laboratory, the UCS, for example, we had an axisymmetric stress condition in which S3 was equal to S2. So in that case, we didn't see the influence of having a true three-dimensional state of stress with S2 equal to S3. And that additional variable is going to define the first one. In this case, let's imagine that direction 1 is actually the vertical direction. So in this case, beta is going to be the dip. The additional variable is going to be the strike. And what we see in this example is that according to the shear strength and also according to conservation of energy and minimization of work, least amount of work, the direction in which I should have this fracture is such that when it moves in the direction not only going down, but also in the direction of the minimum principal stress, S3. And that's why this line, in this case the strike, is perpendicular to the direction of the least principal stress. This is the direction at which the ideal fracture is going to form in 3 dimensions. It's not going to occur at any other orientation, even with beta being equal the same, because that does not that is not the case for the least amount of energy when this block moves and fails. The configuration that grants the least amount of energy is the one with the strike perpendicular to S3. So, with those, then considering those facts, now we can calculate what is beta and what is also, in this case, the strike of the fault, considering a three-dimensional state of stress. And depending on the direction of S3, I'm going to have the direction of the strike. So let's see this for this general case in which, notice that here, this could apply to any condition. It's just written in terms of S1, S2, and S3. This is going to be always valid. Let's apply it to normal faulting, strike slip, and reverse faulting. And this is what is next, figure 519. Let me open it here in a separate tab, where we get what are the ideal orientation of faults for these 3 cases. In all cases, considering that the friction angle is equal to 30 degrees, So the angle beta is going to be equal to 60. And in all cases, also I'm considering that SH mean is in the direction east-west, which this is just an assumption. In the field, you could have this to be different. For example, in the Permian Basin, SH mean is in direction north-south. This is just an example, all right? So let's go with the case of normal faulting. According to what we have seen, then let me just get the normal faulting case so we don't get distracted with the other ones. And actually, let me pop up here another window which is going to have the ideal orientation for the general case, which is right here, and this one. Okay. In this particular case, for the normal faulting and with the assumptions that I have, it happens that the example here on the left coincides what the stresses I have on the right, S1, S2, and S3. For this particular orientation of the stresses and this particular friction angle, I will have that the dip is equal to beta and is equal to 60 degrees, and the strike is equal to 0. And not only that, but I have also a conjugate solution, which is the other plane, number 2. So number 1, for example, has a dip that goes towards the east. But number 2, which is the conjugate solution, has the same dip, same strike line, has a dip that goes towards the west. And let's use this in order to draw stereo nets. This is what you would see, that the two strike lines are going to go north-south, but fault number 1, let me try to fit everything into here, the same window. Fault number 1, we see is dipping towards the east. So if it's dipping towards the east, that means that the pole is going to be here. Number 2 is dipping towards the west, so the pole or perpendicular line is going to intersect the lower hemisphere projection here, and you see that also the pole is at the location of the dip, which is 60 degrees. Notice again that the strike line entirely depends on the orientation of this case of SH mean. And here I have also the Mohr circle, that this fault is happening because it's failure in shear, and this is going to happen at this location. We'll talk more about the Mohr circle later on. Let's go to the strike slip case. In the strike slip, now the maximum horizontal stress is in north-south direction in this case. The minimum principal stress is SV. All right, so I know that these angles of the plane of failure with respect to the plane of the maximum stress applied, here hatched with these lines, is going to be 60 degrees. So now notice that beta, opposite to what we had before, in which beta was a dip, in strike slip, beta is going to define a strike and the strike angle. For example, for number 1, the red one, the strike is going to be this angle, which is actually the complementary angle of 60 degrees. So 60 is here, therefore this one is a complementary angle, which is 30, and the strike is going to be 30 degrees from the north towards the west. And for the green fault, that's going to be 30 degrees from the north towards the east. And in order to comply also with the rule of the plane of the fracture being perpendicular to the direction of the least principal stress on the intersection of this plane, you can see that this line is perpendicular to the direction of the least principal stress, and that's what determines the dip. The dip in this case is equal to 90 degrees, because this is the angle that results in the least amount of work as this fault moves down and moves doing work against the minimum principal stress, which in this case is SH min. Another way of seeing this is that the plane of the failure is going to contain the intermediate stress. So let's come back over here, and this in this plot is a little bit easier to see. That notice also that for this least energy configuration, the plane of the fault, either the red or the green, is parallel to the intermediate stress. And because we know that principal stresses are all perpendicular to each other, also that makes it that plane at that intersection to be perpendicular to S3. So in the strike slip case, as long as the vertical stress is a principal stress, the dip is going to be 90 degrees. If we take a look at that in stereo nets, we'll see something like this. And you may wonder now why we see two dots. Well, I'm assuming here that the dip is exactly 90 degrees. So if the dip is exactly 90 degrees, then this strike line, the red, is going to go from here to there, following my cursor right now. And since it is exactly 90 degrees, it could be either here or there, because both of these are possible solutions are 90 degrees. If I have 89 degrees, then probably just going to be on one side and not in the other. For the green one, the strike line will go through here. But remember that many times we do not draw these strike lines in the stereo net, but here I'm just showing the strike line, which is going to be perpendicular to the line that goes from the pole to the center. And also same thing, I'm plotting 2 points because I'm assuming this is exactly 90. So I'm putting those 2 dots in the stereo net right here. And for the Moore circle, something similar, but now notice that the order of the stresses, sigma h max and sigma h min, failure happens here. We'll come back to the Moore circles later on. Notice that this thing is exactly the same as that one, but now this one I have rotated this, and you could say that I flipped it so that this face is now laying horizontally in order to match this plot. Well, it's not only that, but I lay this tower horizontally and then rotate it 90 degrees, and then that's what you observe here. It's actually exactly the same, but rotated in 3 dimensions. And it is always going to be the same. For reverse, is also going to be the same. Now for reverse is the case in which I flip this and I just make it lay down with this part on the horizontal plane, and now we have the S1, S3, and S2. Okay, wait. Let me correct what I just said. In this case, is the one strike slip in which I make this one rotate and just lay on this plane, on the horizontal plane, in order to be equal to this one. So S2 is going to be vertical, and in order to get to the reverse case, I flip this, make it lay down on this plane, and then rotate it 90 degrees, so I make S3 point up, and it's that case. But it is exactly the same, but just rotated in 3 dimensions. And in the reverse case, as we have seen, we're going to expect fault planes which have a slope which is relatively gentle with respect to the horizontal plane, but the 60-degree angle still applies. Now, this beta is measured from the vertical plane, and this is where beta is, same from here or for there, And we also see that in this case, the intermediate stress, SH mean, it's contained in the plane of the fault, and the intersection of this line, for example, with the direction of the minimum or least principal stress, they have to be perpendicular to each other, and that's what in this case gives me the strike. So in this case, the dip is equal to 90 degrees minus beta, and the strike is defined by the direction of the horizontal stresses, SH max and SH min. What is going to be the strike in this case? Well, the strike lines are going to be the same, and it's east-west in those two cases, and as we said, the dip is going to be 90 degrees minus 60 degrees, which results in 30. If we take a look at that in the stereo net, it will look like this, where the strike lines are, let me move up a little bit, the strike lines are east-west, the same for both, and the poles are here for number 1, which is dipping towards the south, and here for number 2, which is actually dipping towards the north. Remember that this is a common mistake that I always see, to put the pole in the direction of the dip, and it's actually the opposite. Okay, so it is the same thing then with the Mohr circle, and for the Mohr circle now we have the 3 versions, and now just let me show the 3 of them together. But these 3 cases are just application of this case with stresses oriented in different directions, but they are actually they're all the same, and they just have different stress orientation, which results in different orientation of strike and dip. Okay, so this is what how we explain the formation of a brand new fault, and how we can explain its dip and its strike. And again, this is very useful for predicting the geometry of the fault that you might expect to happen if it's relatively young. And also you can use these tools to figure out what is the state of stress at a given location, if that state of stress is causing the faults that you're seeing in nature, and at that exact time too.